Hi, real quick before the video starts, I just wanted to mention who is doing each part of the video. So the project introduction is done by me, Saket. The code walkthrough and demos is presented by Aiden, and the web interface is presented by Ben. Okay, I'm Saket Reddy, and I will be introducing our project, Climate Critic. So first of all, when we made this project, we knew we wanted to have a real world impact with it. And so the premise behind this project is raising awareness about climate change. Climate change is a massive problem that we're of course currently failing to fix, and many people simply don't realize how severe the problem is. So our project consists of two regression models that allows users to see how global carbon emissions really affect Earth's global temperature. So using our linear regression model, users can enter a possible value for global carbon emissions and then see how much the Earth's global temperature would increase as a result. Then using our polynomial regression model, users can enter how many years in the future they're interested in and see what the global carbon emissions would be like at that time if humans keep polluting at the same rate they currently do. So using both of our models, users can really see the relationship between time, carbon emission, and global temperature for themselves. And so they can really see the severity of climate change. Now, in order to accomplish this, we use carbon emission and temperature datasets from Kaggle. Okay, so next up is the code walkthrough and demos. We do know the rest of this video is fairly long though, so here are some kind of more important timestamps, such as the timestamps for where the demo specifically happened. So yeah, feel free to use these as needed, just so you can like keep track of things or look at specific things that you want to look at.
Okay, here's the code overview for the, I guess, machine learning aspect of the entire project. We have a linear regression model, a polynomial regression model, and a work in progress random forest regression model. Okay, so we'll go in chronological order of like how these functions would be called when we run the code. The first function that would be called is process data here, and essentially that just takes in data from this CSV file right here, which if we go to the top, we have years, emissions, and lowest, which is going to be the degrees Celsius. Lowest is just the way NASA, I guess, like manipulated their data. They use the lowest, and then our emissions will be in gigatons per carbon dioxide, or gigatons of carbon dioxide, and then years is just every single year we have a value for. So we have a value, we have our emissions in the lowest for every single year from 1880 to 2023. So our data is very accurate. So the process data function takes in that CSV file and it puts all the data into tensors. So we have our emission tensor and our temps tensor because that's the easiest way that we can use, like, manipulate this data to train linear regression or polynomial regression models. Is just tensors is the easiest way to store the data. But with 2D data, for the linear regression model at least, it's pretty straightforward. You probably could have used an array or something, but tensors was a little bit better, and it was an opportunity for us to learn a little bit more. So next, we split the data. So we have our tests and our training sets. So we train on 80% of the data and then test on 20%, or it depends on how much what value you put in, because when you call this function you specify the test ratio. So in the main function, you specify what you want your test ratio to be. Standard practice is 80-20, and I think that's what we did in this code. I'll have to look, I don't really recall, but here's the linear regression function. So essentially what this does is it calculates the covariance over the variance, and then it calculates a intercept for it. So let's walk through it. So our mean is going to be the summation of all of the values in the X tensor, which will be the emissions tensor, or the summation of all of our values divided by the number of elements, which is very standard. And then mean for the Y would be temperatures. This is going to be our dependent or independent variable. Right, this is our dependent variable. X will be our independent variable. So this is a summation of all of the values divided by the number of elements, of course. And then the difference, X diff and Y diff, is going to be the difference of every element and the mean. So it computes like how different the mean is versus each individual value to get the variance and the covariance. Then we put those into tensors because that's how we're storing our data, and everything has to be uniform, otherwise it won't work correctly. So our numerator is going to be the covariance between x and y, so the amount of variance that they have, so that how much they really affect each other, how much the change in x affects the change in y. And then our denominator is x versus x, so just the variance, how much x changes, which is essentially just like how spread out the data is. So then that's our numerator and denominator, and as we know, we can just divide those to get the slope of our line, which will be the numerator divided by the denominator, of course. And then to calculate our intercept, our y-intercept, of the for the regression line, we take the mean of the y data minus the slope, and then we multiply it by the mean of the x data, which is also standard practice in linear regression. And then we return the slope and the intercept so that the user can use that however they would like. The tests. So this is to test the data. So first we train the model on the training set, and then we train the model, or then we test using the testing data. We run that through the model and we see if the predictions were correct versus our, so we actually have like the real values here. So like say our testing data was from 1980 to 2023. So we would train on every year from 1880 to 1980. And then we would plug in these values from 1980 to 2023. We would plug in the emissions, and we would see if those temperatures that we get align with the temperatures that the linear regression model predicts. So if we go down here, this is our main function. This is where most of the like um, user experience would happen, right? There would be just communicating with the main. So as I said, our test ratio was 0.2. So let me go back. I don't know what just happened. So as I said, our test ratio was 0.2. So we're testing on the wrong file. We're testing on 0.2% of the data, and we're training on 80%, which is very standard. Um, and then we get the mean squared error, right? So that's what the test model um, outputs, and this is our mean squared error function. So essentially, it just takes the summation of all of the differences, and then it squares them and divides it by the length of how many predictions there are. So the reason that we square it is so that the data is exaggerated, so that when we have a large discrepancy, it appears more and it affects the mean squared error a lot more. If you just did mean error, then if you have like a bunch of values that are completely correct and then there's like a small set of values that are incorrect, you won't really notice that because you're not like exacerbating the inaccuracies. So this is just so that we can make the model extremely accurate. And if we go back to the file, we'll see. So we use the mean squared error to print it, obviously, because we need to know if it's accurate. And then I wrote this to test to see if some of our values were correct. So this would be testing on 2023, right? Because if we go to the data, or it'd be testing on 2022, 37.15. And then we print it because I was just wondering what it said. And this is where the user interface happens. In this part of the code, we have a more structured like HTML and stuff that we intend to implement, but this is how I'm going to show you in the demo right now is so the user, I'll just show you. So the user is going to be prompted. Let me go over here. So the user is going to be prompted to enter the emissions value. So we enter an emissions value, let's just say 20 gigatons of carbon dioxide, and that's going to add an additional 0.81 degrees Celsius to the environment. And this is calculated by taking the user input and their emissions, and then we're adding it to 40.9 because that is how many emissions, how many gigatons of carbon dioxide there were in the year 2023. So we need to add it to 2023 because that's going to be additional, right? It compounds. So if we just took the raw carbon dioxide value, the prediction would be wildly inaccurate because there is already existing carbon dioxide in the atmosphere. And then since the user is only concerned about how much their data affected the temperature, we subtract the temperature from 2023 from the predicted temperature so that we can get the difference, solely just the difference between what they inputted and what the temperature currently is. And then it returns the predicted temperature, as you can see, 0.81 degrees Celsius. And if you want to exit, you just type exit. And to run this, you say cargo run bin linear regression and features CUDA. And then let's go to the polynomial regression model. I'm gonna do a little bit shorter because this video is kind of getting a little long. So we have reads data. It's essentially the same thing as the process data function, but we use a different. We use N algebra, which we use their matrices and vectors because using the tensors was like a little bit complicated and unnecessary, honestly. But for later intention, like to implement random forest and maybe a neural network, you would definitely want to be using tensors. So that's for timelessness of your code, but for all intents and purposes, it was just unnecessary. So here we have split data. It's pretty much the same thing. Splits it into testing sets and training sets. And then we need to build the polynomial features before we can actually do our polynomial regression. And this builds a matrix of polynomial features from a single variable input. And our arguments are x, the input data, and as a matrix, and then our degree of polynomial features that we want to generate. And this will return x poly, which is a matrix where each column represents x to the power of the column index. And this is our function that does the polynomial regression. Is pretty short because an algebra has a lot of built-in capabilities that we've used. And so this actually performs all of the polynomial regression. It uses the normal equation in Cholesky decomposition, which is, I'm not going to go into depth on that because we don't have enough time, but it's very standard for simple polynomial regression models. And then it returns a vector of coefficients for the polynomial model that can be used in the main function, which we use the coefficients to calculate the output value. Okay, so down here we have, hold on, I actually have to get rid of this because this was for a test and it will throw an error. Okay. So now that we have that, let's command. Okay, what just happened? Okay, I do not know what's going on. Okay, there we go. Okay, so we're gonna go back into the polynomial regression model. Sorry about that. So in our main function, we have here, okay, so the for loop's on. Okay, good. Okay, so we read our data, split the data, of course. We only use degree 3 because when I run it, I'll show you our degree 3 coefficient is actually 0. So it was degree 3 is all we needed. If we just kept going, the degrees would be 0. It would be unnecessary. So we validate the model, print the performance, and we prompt the user for input, and then we print their predicted input. And of course, we have our mean squared error again. We have mean error and mean squared error in this code, but mean squared error is the most important. And then if we go here, we can run this by saying run cargo run bin poly features CUDA. And so we have here, as you can see, this is the mean squared error. It's 2.9. The mean squared error of the linear regression model is very, very low, which is exactly what we want to see. It's 0.170. Honestly, can't get lower than that. I don't know how you could possibly even get lower than that. It might even be more accurate than a neural network. Mean squared error on the test set is 2.19, which is fairly low. For how large the values are, that's pretty low. But obviously it could be improved. And as you can see here are the coefficients. We have the 0th, the 1st, the 2nd, and the 3rd, of course, which is 0. So there would be pointless to have more coefficients than that. And the point of this model is to predict the amount of emissions that there are going to be in a year, in any given year. So like if we go back to the data set, so this only goes down to 2023, right? So if we wanted to predict the data for or the emissions that that is going to be in 2024, we would have no way of doing that. And so that's why we implemented the polynomial regression model, because if we just say 1, which is going to add the year to the current year, well, not the current year, but the year that we have in our data, which is 2023, 1 will add it and become 2024. So now we have 41.45 gigatons of carbon dioxide. And if we go back to the data, that looks pretty accurate, and it looks like that's probably what we would say. The reason that it's not as high of a difference between 2022 and 2023 is that carbon emissions are actually like the amount of change is actually going down in recent years because we've started implementing efforts to minimize carbon emissions. So that looks good and looks pretty correct. And as you can see, our mean squared error is 2.19, so we know that it's correct, and we can exit by typing exit again.
Okay, so that was the main part of our project. But we actually were able to get that main part done a bit early, and so we tried to expand the project a little bit. Basically, we found a data set with a whole lot of carbon emitting behaviors. So, for example, things like what your home's heat source is or how often you fly. It was a data set with a lot of these data points, and it told us the total amount of carbon emissions these carbon emitting behaviors would produce when taken together. And so we try to expand this project by building a web interface where users could answer these questions, such as how they heat their home or how much they fly and things like that. And then this data would be fed into a random forest model, which would then take all this data and figure out what the total carbon emissions this person would contribute to the environment over their lifetime. Unfortunately, we didn't have enough time to finish this. However, we still thought it was interesting, and so we still wanted to talk about it in the video, and some of the code is still in the GitHub. So this is not part of our final submission, it's just kind of an extension, but we wanted to talk a little bit about it anyways.
And then our last function, or our last code file that we were working on is the random forest regression. So this is very, very complicated stuff. Random forest regression essentially makes a forest or like a tree of a whole bunch of subtrees. Well, that's why it's called a forest, because you have one node and then you have just a bunch of subtrees. And each tree individually is a model that works off of its independently. They're all independent of themselves, and each tree is trained on different portions of the data. And then, so you just have a whole bunch of models that are trained off of a whole bunch of small portions of the data, and then you feed in your input to the root node, and it feeds it to each independent tree, and each tree will return their prediction, and it averages all the predictions, and that is the root node's final prediction, right? So the benefit of doing that is you have very generalized outputs, right? Because you have just a bunch. It's trained on a bunch of different parts of the data, so that your output is going to be very, very accurate. So it's called an ensemble approach, and that's why it's called random forest, is because it builds a forest of trees, and each tree is independent of a different tree, and we get our response, which will be our prediction. But as you can see, it's a very short code file because it's very complicated stuff, and most of the time was spent researching. I had to research a bunch of stuff to even understand how it worked, and then I started working on implementing it in Rust, and then finals came around. So if we had more time, ideally, we would like to finish the regression or the random forest regression. And as you can see, is this this random forest would be trained on a different data set actually, and we have that here. If we go to this file. So as you can see, it's a lot to comprehend, but if you just follow along, in the top, we have body type here, sex, diet, how often they shower, heating source, transportation, vehicles, a whole bunch of stuff. And each row is going to have just somebody who inputted all of their data and their carbon emissions. If you can see my cursor, it's 3,226 is this person's carbon emissions based off of their life that they've lived, with all of these different variables. So our goal was to implement the random forest regression to take in somebody's body type, sex, diet, how often they showered, transportation, how many times or how far they drive a car, how many times they fly by air. And the point was to get an extremely accurate carbon output for how much carbon dioxide they would release into the atmosphere in total in their entire life. And then after the random forest regression model predicts the carbon output, we would input it into the linear regression model to get the temperature, and that's what the user would see. So the user would input, like have a drop down menu, and they would input all of their data, so their body type and stuff like that, and then they would see is the temperature change that their life would have on the world, essentially. And we would do that by using a combination of random forest and the linear regression. And then if we had even more time, we'd implement the polynomial regression model to get the total carbon that's going to be in the air by the time that, like, I guess it's kind of sad, but by the time their life is over, what the current carbon dioxide is going to be, and then we would add their carbon dioxide, so that it's the additional carbon dioxide in the air, and we'd be able to see their total lifetime real effect on the atmosphere, in the atmosphere that we live in. So literally how much that their life would accelerate climate change. And so we didn't really, I didn't really have a lot of time to implement this, but as we can see, if we run this, we need to do cargo, yeah. So this is called RF, and okay, so there's an error. So the code doesn't even run right now, but if I would be able to run it, I would show you the mean squared error currently is, I think it was 950 billion or something last time I checked. So obviously very, very bad, and it needs to be updated. But yeah, some challenges we had were Rust, coding in Rust. Everything has to be very, very, very safe. So if we go here to the linear regression model, it's like the perfect example of what I mean. If we go down to where I'm manipulating all of the tensors, I have to put question marks at the end of every single statement because Rust just enjoys being very, very, very safe language. I even had to make an additional return type for if the code didn't compile. which is good because I didn't run into any errors after I had compiled the code. But getting the code to actually build and run took a very, very long time, and it was not ideal. And if you would like to run the code locally, first of all, you need to have CUDA installed, which requires a dedicated GPU. So it is kind of complicated, just because some of the processes are pretty GPU intensive or computer intensive. So using a GPU accelerates it a lot. And I have a GPU, so I've oriented all the code to run smoothly with GPUs. So if you don't have a GPU, unfortunately, you will not be able to run this code. But you can build it or you can run it. You don't need to build before you run, but building allows you to see like errors before you try to run the code. But yeah, you just say cargo run bin linear regression features CUDA. And for the linear regression, polynomial regression, and random forest, you have to do features CUDA because otherwise the code will not compile. And here's our cargo file with all of our dependencies and our bins. So we have linear regression, random forest, and polynomial regression. And if we go here, we also have another folder called Rocket, which has the handle.rs, which will allow the user, it uses this UI from index.html, and it allows the user to input all their information, and then it would feed it to the model, and we would get um, our output. And to run this, I believe there's a bin. Yeah, there's two bins. So rock, you just run cargo run bin rock, and you don't need any flags or features. And cargo run bin main, and that's how you run the code. And that's an overview of all of our code and all of our data sets. Everything is available on GitHub, and running information is on the run.md file.
Guys, this has been Hug. I'm going to be showing you our UI, which was kind of our extension of this project. Our main focus was on our linear regression model and our polynomial regression models, making sure that worked and making sure it was pulling the data from the CSV correctly. But as a little extension, just kind of see if we had enough time, we were going to use Rocket for our UI to kind of handle post requests. So here in this predict function, you can see like the behavior, frequency, duration that can be pulled from the models, and you can have the result process and return results from the data. Rocket allows us to use HTML, JS, and CSS to kind of structure our UI. So if I go ahead and run this really quickly, just go ahead and see the end of the project and run it. If we open this using live server, just a moment. All right, so here's kind of our UI. They can enter in any carbon emitting behavior. It's like a normal behavior. If you're doing it monthly, duration like 7 days per month, that's where the output would be from the model. So yeah, that's basically how our UI would work. Just kind of our little extension of the project, something off of our main course. But yeah, that's pretty much it.